In 2022, the year ChatGPT was released, researchers at Google began exploring what role large language models might play in robotics. Their first notable result, a system known as SayCan, used a large language model as a planning system to break down complex tasks into subtasks. In this demo, SayCan breaks down cleaning up a spill into the subtasks of finding a sponge, picking up the sponge, going to the spill, and so on. From here, the team expanded on this work, creating a more capable iteration of the idea called inner monologue, and another interesting variant, where the team used an LLM to write code to control the robot on the fly. However, these early efforts were effectively bottlenecked by the available robot controls algorithms. Once the LLM in SayCan decided to pick up a sponge, a completely separate neural network that had been trained to imitate humans controlling robots to perform various small tasks, was used to compute the actual robot control signals. This meant that SayCan was effectively limited to a menu of actions the LLM could choose from. To get SayCan to place a Coke can on an image of Taylor Swift, behaviors involving Coke cans and Taylor Swift would have to be explicitly trained. At the end of 2022, the team made a significant improvement to their control layer, introducing Robot Transformer 1, or RT1. Like the team's previous control algorithms, RT1 was trained to imitate humans, but used a significantly larger dataset, with over 130,000 human demonstrations, and used a larger transformer-based architecture. RT1 was able to perform a significantly broader range of actions than its predecessors. This effectively gave the planning layer a much larger menu of actions to choose from. The RT1 team showed that using the planning LLM from SayCan, coupled with RT1 to control the robot, significantly improved performance on long horizon tasks, like finding certain items in kitchens that the robot hadn't seen before. As Google incrementally improved their robot brains, large language models were also rapidly advancing. The LLM used for planning in the SayCan and RT1 systems was the text-only Palm 540B model, trained in early 2022. This meant that the robot's planning layer couldn't actually see the world. After breaking down a task like helping clean up the kitchen into text subtasks, Google's robots relied on the RT1 control layer to take in images from the robot's camera and iteratively send control signals to the robot's actuators until each subtask was complete. This approach worked fine for some tasks, but having a planning layer that was effectively blind was clearly not ideal. On March 6, 2023, about a week before the release of GPT-4, Google researchers demonstrated Palm-E, a variant of the Palm large language model that directly incorporated images and other data sources. Using the multimodal Palm-E instead of the purely text-based Palm LLM as a planner, with RT1 as the control layer, the team demonstrated a significant expansion in capabilities. Now that the planning layer had access to vision information, the robot could perform more complex tasks that require adaptive planning, like moving objects out of the way to reach a desired object, and fully autonomously recovering from setbacks. Here, a robot using Palm-E as its planning layer and RT1 as its control layer is asked to retrieve a bag of chips. And when a researcher repeatedly puts the chips back in the drawer, Palm-E is remarkably able to recognize that something has changed and adapt its plan. Now, let's zoom out a little and consider the full Palm-E plus RT1 robot brain. Although Palm-E and RT1 were designed to work at different levels of the stack, they have some really interesting similarities. Both models take in images from the robot's camera and use a vision encoder neural network to process the images. From here, in both models, these encoded image representations are passed into a transformer. This is the same type of compute block used fairly universally in large language models. The big difference here is what these transformers are trained to do. The RT1 transformer was trained to directly output robot control signals by imitating humans controlling robots to solve various tasks, while the Palm-E transformer is trained to output text across a wide variety of tasks, including simple next token prediction on internet text, as we see in standard LLM pre-training, but also language vision tasks like image captioning, And importantly, Palm-E was also trained to break apart robotics tasks into smaller subtasks. The similarities between Palm-E and RT1, and the fact that the team was able to expand the Palm language-only model to effectively make use of other types of data, all beg the question, do we really need two separate models here? Why not just continue expanding the Palm language model to not only take in image data, but also to directly output robot control data, effectively absorbing RT1 into a single powerful end-to-end model? Said differently, can large language models, by far the most powerful AI systems we've trained so far, be trained to become robot brains? This brings us to Taylor Swift and the Coke can. In July 2023, a few months after the Palm-E paper came out, the Google robotics team demonstrated RT2. Taking Palm-E and another multimodal LLM known as PALI-X as starting points, the Google team trained these LLMs to directly output robot control signals, training on the same human-controlled demonstration data they had used to train RT1 6 months earlier. And incredibly, it worked. RT2 was able to generalize shockingly well to objects, environments, and tasks that were not in the human demonstration data. This is what makes the Taylor Swift demo so impressive. The robot control training data definitely did not include Taylor Swift. So for RT2 to solve this task, it had to learn how to bring together abstract concepts it had learned in its internet-scale pre-training with the robot control episodes. This means that these models can learn to connect the vast amounts of image, video, and text data on the internet with real-world actions, potentially harnessing the full knowledge of the internet into robot brains. This is why this demo is such a big deal. It answers the question, can large language models be trained to be robot brains? With a shaky but definitive yes. The RT2 team coined a new name for this type of model, Vision-Language-Action, or VLA, linking together vision, language, and action into a single unified model.